Yeah. Good morning, all the students. In today's class, we'll start the second module. In the last sessions, what we have covered, I'll just give a recap and then go to the second module. So all of you ready for the quiz? It starts exactly at 2:40. Connect on time. It will not take more than half an hour. Okay? Yeah. Let's start this first lecture under module 2. And before that, let me give a quick recap on what we covered in module 1. We understood what is a well-posed learning problem, how to understand about a learning problem, how a machine learns about a problem, and how it performs well with unseen data. Right? The machine tries to learn from already existing data, historical data, and it tries to modify its learning or its understanding about that particular historical data, and it tries to generalize its understanding to the future data or new data or unseen data, right? So the understanding is nothing but it is trying to fit the machine learning for that particular data, right? So any data out of that understanding will be a problem for the machine to predict properly. But if we give more and more training examples, it learns more and more better, so that it can generalize well. It can generalize well means it can predict well about the unseen data, right? So how to understand about a well-posed learning problem and designing a learning system also we have seen. Means how to give the training experience, or then how to formulate a target function and how to represent the target function, which algorithm we have to select in order to represent that target function, and finally adjust the weights in order to make that function ideal target function, right? That we have seen in the learning system design. And also we have come across a topic called as perspective. What is the perspective of machine learning? What is its viewpoint, and what are the issues we come across machine learning? And also the concept learning task by taking help of a simple training example set or a simple training set, which gives the climatic conditions of on various days, recorded on various days, and whether your friend will enjoy a water sport or not. Now the machine tries to learn that day's climatic conditions and your friend's reaction to those climatic conditions, whether he enjoyed the sport or not. Based on that, it will try to predict whether your friend will enjoy that water sport given a day's climatic condition, right? That is called as concept learning. It is trying to learn the concept. Concept means always it is a positive example. Remember, do not get confused between positive labels and negative labels. Wherever there is an outcome label called as S or 1 or simply on, in that case we call them as positive examples, right? And if you take no or zero or off, in those cases we take them as negative examples. But it is not restricted that only these three values can be taken. Sometimes you can take COVID patient tested positive or negative. In that case, positive will be your positive class, negative will be your negative class. Cancerous patient. Now, normally we'll give the attribute name as having cancer. Then, so that we can give the labels as yes or no, right? Otherwise, you can just give condition. Then you can give the label as having cancer, not having cancer, like that. The labels may differ based on the attribute you give. Okay, if the attribute is condition, end condition of the patient, outcome of the test. In that case, you can give having cancer, not having cancer, having heart disease, not having heart disease, like that. Okay, otherwise you can simply frame the attribute more meaningfully, having cancer, then you can give yes or no. That will be more easy for you when you are encoding the data. Encoding means you have to transform all the categorical data into numerical data which the machine learning models can understand. That is the main limitation of any machine learning model. The machine learning algorithms or models doesn't understand categorical data, and they don't work well with categorical data. That is why you have to transform them into numerical data and then provide it as training to the model, right? For that sake, in order to encode it easily, better give the target labels as yes or no, right? Now, we also understood how concept learning task is treated as a search problem. Why? Because whenever you're giving a machine that set of training examples, the machine will try to fit among various hypotheses, the best hypothesis that can explain the data combinations given in the training examples, attribute combinations given in the training examples, right? In that case, the machine is trying to search the best solution from alternative solutions available. That is why we call it as a search space. Hypothesis space is a search space, and concept learning is considered as a search task, search problem, because machine is trying to find the best solution, best hypothesis out of the existing hypothesis or out of the all possible hypotheses. Okay, now we have also gone through this find us algorithm. This find us algorithm will try to find the most specific hypothesis that is consistent with the training examples, that applies to all the training examples. And version space. Version space also, version space is a set of hypotheses H which are consistent with the training examples D. Right? If there is any hypothesis that is not consistent with the training examples D, then it should not exist in the version space. Okay, so what is the definition of this version space? Version space is the hypothesis, is the set of hypotheses that contains all the hypotheses which are consistent with the training examples D. Got it? Now, candidate elimination algorithm also we have checked. What is this candidate elimination algorithm? The hypothesis space initially has all possible hypotheses. Then you will try to filter out the hypothesis whenever a hypothesis is found to be inconsistent with the training examples. Means it is not applying to any of the training examples. Then you keep eliminating those hypotheses so that your version space will shrink as small as possible, so that it contains only the most general hypothesis boundary and the most specific hypothesis boundary and any hypothesis lying between them, but they should be consistent with the training examples. So the main line, if we want to explain it in a single line, we can say like this: version space should not contain any hypothesis that is inconsistent with the training examples. Version space should contain only hypotheses that are consistent with the training examples, right? That is the output of this candidate elimination algorithm, right? And finally, we have seen this inductive bias concept. If at all we don't make any assumptions and we try to consider all possible hypotheses in the hypothesis space, then our search will not end. The machine can't learn properly. It can't generalize well on the unseen data, because it will always tell the end label is true for whatever data given, because it contains all the hypotheses that are applicable. Or I'm comfortable with this, or I'm comfortable with this condition also, or I'm comfortable with this category of data also. The machine says like this, if at all it can speak, right? So it is comfortable with this data, this data under the attribute, or this data under the attribute, or this data under the attribute. Or means what? It is okay with any type of data that it will try to predict as yes only. It will never predict as no. That is not a good machine learning model that we want, right? It should also be able to predict sometimes. If there is a negative label, it has to predict it properly. Okay, so you can't consider all hypotheses possible. You have to make some assumptions. What are those assumptions? You can make an assumption like this, that combination of this attribute and this attribute and this attribute. All these combinations have to be true. Only then the end label will be yes. Otherwise it will be no. Means you are giving the disjunction, you are giving the conjunction of the attribute values. Okay, means you are giving more constraints on it. You are making assumption that only conjunctive attribute values will be considered. No disjunctive attribute values will be considered, right? So that assumptions what you make and the training examples given will train a machine in order to generalize well to the future data points or unseen data. That is called as inductive bias. You're biasing your machine learning problem. You're biasing your machine to make some assumptions so that it can generalize well to the unseen data, right? These are the concepts that have been covered in the first module, and I think it has taken a lot of what we say effort from your side, right, to understand this concept. So it will be like a what to say relaxing time for you in the second module. You'll easily understand all the concepts here. There are mathematical problems, but it will not be much complex, right? So focus from the first day itself, first session itself, so that you will easily understand the upcoming concepts. Okay, decision tree is the easiest of all to understand. Even for interpretation also it will be easier, right? So we are going to our second module in which we deal with decision tree learning. Okay, this is very important set of algorithms it has under decision trees. So we need to understand the basic concept so that you can know which data will suit to apply this decision tree model and all. Okay, and what are the appropriate problems for decision tree learning also, that we are going to see. Now for your first internal, your case study question will be from this decision tree chapter, and I'll tell you what type of question will come. And for your innovative question, you have presented your knowledge about unexplored areas of machine learning, right? So that common question will be given. Whatever study you have made in order to make that presentation, same you can you can present in the exam in your own words. Okay, that will be your innovative question. So I'm not going to give you something entirely new concept because the time is limited. You can just present your knowledge, what you have already acquired about unexplored areas of machine learning, right? Whatever you have understood in order to present in the activity time, same thing you can present. Okay, now let's get introduced to this decision tree learning. Decision tree learning is one of the most widely used practical methods for inductive inference. Now you're well aware of this inductive inference, right? Can anybody tell me about inductive learning in a single sentence? Students? What is inductive learning? I have given very simple definition, right? Inductive learning is given the observations, you can infer rules from it. You can formulate rules from it, right? But deductive learning is rules will be given to the student or to the machine, and it will try to learn the concept from that rules, or it will try to learn about those concepts practically by implementing those rules, right? That is called as deductive learning. So inductive inference is given the training examples, given the observations, or given the training set, it will try to infer some rules. It will try to conclude, or it will try to draw some rules out of those observations, right? That is called as inductive learning. Now decision tree learning is one of the most widely used and practical methods for this inductive inference. It is a method for approximating discrete valued functions that is robust to noisy data. Important characteristic of decision tree. It is robust to noisy data and capable of learning disjunctive expressions. In our previous chapter, what assumptions did we make? The data should be free of noise, means it should not contain missing values, it should not contain duplicate values, it should not contain any outliers. That is our assumption, right? So that means we are considering for that machine learning techniques only robust data, not noisy data. But this decision trees allow us to give noisy data also to the machine. Means they're robust to noisy data. Though noisy data is present, it will not deviate the accuracy or performance of the decision tree models. Okay, it is robust to noisy data. This is the important characteristic of decision tree. It is robust to noisy data and capable of learning disjunctive expressions. What is the assumption we have made in inductive learning in the last part of first module? We assume that, the machine assumed that only conjunctive expressions are allowed, right? But here, even disjunctive expressions also will be entertained by the decision tree model. Though the learning time will increase in order to learn each and every hypothesis possible, still they perform well because it is giving more freedom to the, say, learner in order to learn the hypothesis. Okay. And ID3, assistant C 4.5, CAT 4.5, right? These are decision tree learning methods that search a completely expressive hypothesis space and thus avoid the difficulties of restricted hypothesis spaces, right? That is our limitation in the previous chapter. Our limitation is the hypothesis space, if it is highly expressible, then other type of problems will arise. If the hypothesis space contains every possible hypothesis, then other types of problems will arise, such that the machine learning model will not be able to generalize with the new data. Because it is okay with any type of attribute values, it can't predict well with the new data. Sometimes it predicts well and sometimes it fails to predict properly, right? Now that kind of difficulty can be overcome by using this decision tree algorithm, because that is what is given here. Thus avoid the difficulties of restricted hypothesis. You need not adjust with restricted hypothesis. You can give all possible hypotheses. Now the decision tree model will be able to generalize the hypothesis from those all possible set of hypotheses. It will reduce the hypothesis space from learning all possible hypotheses. Then what is their inductive bias? We understood that decision learning models can entertain disjunctive combination of attributes or conjunctive combination of attributes and, right? Now, what is their inductive bias? We understood that every model, every machine learning model should have some inductive bias, right? Now, otherwise they can't generalize properly, right? Now, what is their inductive bias? What is decision trees inductive bias? What assumptions do we make with respect to decision trees inductive bias? A preference for small trees over large trees. It always prefers smaller trees rather than large trees. That is the inductive bias. You will come to understand what is this, why it prefers small trees over large trees, why it will try to learn from small number of trees rather than using large number of trees, and why it is treated as their inductive bias. That will gradually understand as you proceed with further concepts of this module. Okay, now let's understand more better about this decision tree algorithms. Now this decision tree learning is a method for approximating discrete value target functions in which the learned function is represented by a decision tree. Understood? In our first chapter, when we considered playing the chess problem or playing checkers problem, there our target function is a real valued function. Do you agree with me? We have a target function v such that we have a weight w0 plus w1 x1 plus W2, X2, and so on, right? This is a real value target function. Okay, you are getting some value there. You're getting some numerical value there as an outcome of this target function, right? That is the solution which is given to this equation. That numerical value is the solution for this particular equation that fits to the training example. Now, what is discrete value target function? If you are mapping all your instances either to 0 or 1, or you're mapping all your instances either to yes or no, means there is discrete value. Discrete means it is not continuous, they are separate, right? 0 and 1 are separate. Are you having 0.1, 0.2, 0.3? If you are having 0.1, 0.2, 0.3, then they are called as continuous value target functions. But if you are having 0 and 1 separately, clear demarcation is there between the values, yes or no separately, then we call it as discrete value target function. Okay, now decision tree learning is a method for approximating discrete value target functions in which the learned function is represented as a decision tree. So a decision will be taken at each node and it will direct to its leaf node. Again, a decision is taken at this subroot node and it will lead to further leaf nodes based on the decision taken at that particular node. Okay, this is the basic notion of a decision tree. Now, learned trees can also be re-represented as sets of if-then rules to improve the human readability. Correct? If a condition is true here, yes, go towards this leaf node, no, go towards the other leaf node. If a condition is true at this node, if yes, go towards this leaf node, no, go towards this leaf node. What we are trying to do here, we are trying to infer some rules. Now, it's the same decision tree can also be expressed in the form of a rule, right? If yes, then do something. If no, else means no, then do some other thing. Right? We are trying to write it in the form of if-then rules. Okay, so all decision trees can also be re-represented as sets of this if-then rules which can improve the human readability. You can easily understand what is happening underneath, okay, which you can't do with other types of target functions. Where numerical calculations are being done, you can't easily understand what is happening behind. But in a decision tree, you can understand it as, you can understand it in the form of if-then rules. You can interpret it in the form of if-then rules, right? Now, these learning methods are among the most popular of inductive inference algorithms. That is why it has become so famous. It is the most popular of inductive inference algorithms. Inductive inference means the machine is learning from the observations and inferring some rules or inferring some conclusions or inferring some statements. That is called as inductive inference. These algorithms have become famous for their inductive inference. They learn very well from the training examples and try to infer some rules as conclusion. Now, what are its applications? Where do you use this decision trees? In diagnosis of medical cases, whether you, if you want to predict whether a patient acquired a disease, whether a patient got a disease based on his symptoms, where symptoms are the attributes. Then you will try to predict whether a patient acquired the disease, yes or no. Or when you are assessing the credit risk of a customer, this is a financial behavior of the customer. He repaid his previous loans very well. He has a own house. He is married and he has a stable income. These are all the attributes. Now, such kind of training examples are given to the machine to learn from, and after it has learned, if a new customer's data is given, it will be able to predict very well, right? If the customer is married, yes, then if he has a own house, yes, then he has paid the loan. If the customer is married, no. Then if he doesn't have an own house, he defaulted the loan, he didn't pay the loan. Like that, different set of conditions are checked, and finally the label will be predicted whether he is a reliable customer or not, right? Or predicting whether a transaction is fraudulent or not, predicting whether an insurance claim is genuine or not. All these are applications of decision trees. Now, how do we represent this decision trees? It is like a simple game what you play here with respect to decision trees, right? You always write a condition. S means do this, no means do this, like that. Okay, it's very simple. Decision trees classify instances by sorting them down the tree from the root to some leaf. So root will start here, and S, do this, no, do this. Again here, S, do this, no, do this. It goes as far as possible until it can classify all the training examples, all the instances correctly. I'm not telling training examples because it will actually classify the test examples. That is unseen data. Okay, so whenever some new instances are given, whenever some unseen data is given to the decision tree model, then it will start with a better split where it can split the data into two categories. Then it applies some more condition and splits them more better, and then it applies some more condition, splits them more better, so that the final classification should be noise free. Final classification should not have any impurity. The data or the classes have to be clearly classified. Pure classification should be obtained. All these terms you will come across when you are learning about other concepts of under this decision tree. Okay. Now each node in the tree specifies a test. That is what I told, right? It is a condition. It specifies a test of some attribute of the instance. Means where do you apply the conditions? On which variables do you apply the conditions? Obviously attributes only, right? If the sky is sunny, yes. If the humidity is low, yes. If the forecast is doesn't change, no, right? So you are applying the conditions on the attributes. And each branch descending from that node corresponds to one of the possible values for this attribute. Okay, so if you start like this, S means go to this, no means go to this. It is descending. The branch, each branch will descend from that particular node corresponding to one of the possible values for this attribute. Okay, now an instance is classified by starting at the root node of the tree, testing the attribute specified by this node, then moving down the tree branch corresponding to the value of the attribute given in the example. Okay, if we give income is greater than 5 lakhs, yes, go towards this, no, go towards this. Now if owns a house, S, go towards this, no, go towards this. So based on the root node's condition, it branches towards its leaf nodes. Okay, this process is then repeated for the subtree again, rooted at the new node. This is a subtree. When you take a tree, this is the root node, this is the child node, and if you consider this part, this is a subtree. Okay, and this is called as depth of the tree. The depth of the tree here is 2 because there are 2 layers. Okay, and how many nodes are used here? Totally 1, 2, 3, 4, 5 nodes are used, but that doesn't matter. Normally we take the depth only. Depth and the number of trees considered are the main attributes. Okay, let us not go into that depth. Let us understand it in the initial sense first. Once you are confident with this fundamental representation, I think we can go for complex concepts. Okay, now if this kind of new instance is given to a model which has built its decision tree from the training examples. Let us consider this is the decision tree that is built by the decision tree model by learning from training examples, right? Now, what tree it has built, let us see. If we are taking again same kind of example, whether tennis can be played on weekends. Okay, that is the problem. Let us consider the problem as whether tennis can be played on weekends given some climatic conditions. Okay, now the training examples contain on these days climate is like this, they have played tennis. On another day climatic condition is this, they have played tennis. On another day climatic condition is this, they didn't play tennis. Okay, so machine will try to construct a decision tree from these training examples and try to generalize it for an unseen data. This is the unseen data. Okay, now let's see what is the tree constructed. If the outlook is sunny, means the weather is sunny, and further if it is humid and the humidity is high, they didn't play tennis most of the time. But if the outlook is sunny and the humidity is normal, then they have played tennis. There is proof from the training example that they have played tennis. That is why the machine learning model has constructed this tree. Now, if the outlook is overcast, overcast means cloudy. The sky is covered with clouds. These are some fancy words that they use, but okay. You also try to use them only. Okay, but understand the meaning behind that. Now, if the outlook is overcast or cloudy, then they have played tennis irrespective of other weather conditions. Okay. Now, outlook is rainy. The weather condition is rainy and the wind is also strong. In that case, they didn't play tennis most of the time. And if the wind is weak, as they have played tennis in the rain also. Okay, this is the decision tree constructed by the machine learning model based on the training examples given. Now let us see about this unseen data. What is the data given? Outlook is sunny. When outlook is sunny, what is the path taken by the decision tree model? This path, right? Now when the temperature is hot, temperature is not given here. Okay, let us assume that let us not take this because in this decision tree temperature is not given, but let us construct it, or we can construct another branch here where it gives temperature also, so that if the temperature is cool, if the temperature is cool or if the temperature is hot, okay, then let us say they didn't play tennis on this day and they have played tennis on this day. Okay, now our rotation tree is covering this example. Outlook is sunny, yes. Then let us take here sunny. Outlook is sunny, yes. Temperature is hot, then yes, they have played tennis. But there are further some conditions to be checked. What is that? When humidity is high, they doesn't play tennis. When wind is strong, they doesn't play tennis. Like this, conditions will be given. Now, I give a new data set for you. These are various conditions they have discussed, not the unseen data, but various conditions they have given. If outlook is sunny, then through which branch this goes? Here and here. If temperature is hot, it goes through this branch. If humidity is high, it goes through this branch. If wind is strong, it goes through this branch. That is how a machine decision tree model is guided. Now, if a new data is given like this, note down what I'm telling and you have to tell me what will be the outcome. If the outlook is rainy, outlook value is rainy and wind is weak. Outlook value is rainy and wind value is, attribute value is weak. Do they play tennis or not? Students, answer me. When the outlook is rainy and when the wind is weak, what is the prediction based on this decision tree?
They play,
Yes,
ma'am.
ma'am.
Yeah, they will play tennis because this is the path followed. Outlook is rainy. Yes. Wind is weak. Yes. They play tennis on those days. That is how the decision tree will take decision about a new data point that is given. It makes prediction about the new data point that is given. Okay. Now in general, decision trees represent a disjunction of conjunctions. What is the time?
9:12, ma'am.
Okay, we have sufficient time. Yeah, in general, decision trees represent a disjunction of conjunctions. Disjunction of conjunctions means I'll represent it here. A and B. This is a conjunction, right? Or B and C. Or D and E. This entire thing is called as disjunction of conjunctions. Means conjunctions are taken and or is applied between them. Okay, this is called as disjunction of conjunctions. So any decision tree if you take, it is a combination of disjunctions and conjunctions. It is actually disjunction of conjunctions, right, of constraints on the attribute instances. Now each path from the tree root to a leaf corresponds to a conjunction of attribute S and the tree itself to a disjunction of these conjunctions. Let us take an example, you'll understand more better. Now see this first line, outlook is sunny and humidity equal to normal, right? Then they will play tennis. We got S for the first bracket, right? Or another scenario is given. Outlook is equal to overcast. They play tennis. So it is S. Or what is the last one? Outlook rain and wind is weak. They play tennis. So what is the overall result? What does this be interpreted as by the decision tree? Yes, they will play tennis. Okay. So how is this decision tree represented? All along this path, entire single path, if you take right from the root node to the leaf node, if you take a single path, it is called as conjunction. Outlook sunny and humidity is high. We are using and, right? That is along this path. That is why we call it as conjunction. Now we are also considering this one. Means there is a branching here. Whenever there is a branching, we call it as disjunction. Got it? So whenever you're following this path, outlook sunny, humidity normal, this is conjunction. That is why we have used and here. Now, when there is a branching, you're going to the next condition. That is why you have used an or here. And whenever there is another branching, you have used or here. But within this, you have used a disjunction along this path. Outlook is rainy and wind is weak. That is a conjunction again. Okay, so whenever you take a decision tree like this entire path can be represented by a conjunction and conditions. And this is true, and this is true, and this is true. That is this entire path. But or, if it is not this case, or you go to the other branch, this part, that is given by disjunction. That is or. Okay, this is how you need to understand about decision trees. Now, what are the appropriate problems where this decision tree learning is applied? Instances are represented by attribute value pairs, categorical as well as numerical values. If they are represented as attribute value pairs means we have seen here wind equal to strong. That is attribute value pair. Humidity equal to high. That is one attribute value pair. Humidity is the attribute and high is its value. That is why we call it as attribute value pair. Humidity is the attribute and high is its value, right? All these instances are represented by this attribute value pairs only, whether it is a categorical or a numerical, right? In that case, in such cases, say if the patient cough condition, yes. If he is having a cold, yes. Means cold is attribute name and S is the value. In that case, we call them as attribute value pairs. Now, if there is data which we can represent as this attribute value pairs, then this decision tree is suitable for that. And the target function has discrete output values. Target function has labels, outcome labels as yes or no, whether a customer is reliable or not, whether a patient is positive or negative, or whether heart disease is acquired, yes or no. These are all called as discrete output values, 0 or 1. These are called as discrete output values, not like numbers. They are like categories. Okay. In that case, whenever the target function is discrete output value, then immediately you can go to select decision trees. But there are some issues. Whenever you outright select decision trees, something else like overfitting and underfitting may happen. That we are going to discuss in the last concept of this chapter, and that is very interesting concept. And a good machine learning expert doesn't allow models which are overfitting. So if you want to become a good machine learning expert, you have to know those underlying concepts. Okay, so you have to focus properly. Now disjunctive descriptions may be required, where you have to check conditions like this is true, or this is true, or this is true. In such cases, you can branch with the decision tree. You can give various branches for or conditions, right? And the training data may contain errors. If your training data is noisy, if your training data is having outliers or extreme values, if your training data is having missing or duplicate values, then we call that data as noisy data. Now that data can also be dealt with by using decision trees. Decision trees are robust to outliers. Decision trees are robust to noisy data. Okay. So when you're not confident about the cleanliness of your, when you're not having confidence about the cleanliness of your data, in that case, you can go for decision trees. Okay, they can bear with noisy data. They can afford noisy data. Now the training data may contain missing attribute values. That is what I said, right? If there are any missing attribute values, still the classification may not deviate as it does in other machine learning models. So in that case, you can go for decision trees. Now let's try something different. Now you understood how to represent a small decision tree, right? Now I will ask you, your case study question is based on this, listen carefully. Now I will ask you to construct a decision tree for Boolean expression A and B, or I can simply write it as A and B. Can anybody tell me, or you can guide me drawing this decision tree, right? Now I am taking a root node with A's condition, right? How does the truth table look like for AND expression? Result 0, 0, it will give 0, 1, 0 will give 0, 0, 1, again 0, and 1, 1 will give you 1, right? Now, making use of this truth table, can you construct a decision tree for A and B? Can you try it out for 1 minute? Did you get the idea how to construct a decision tree? Simple now, right? You can construct a decision tree for A and B. Now tell me what I can do. Shall I branch from here? Can any student guide me in this? Now, if I take A as the root node, I have two conditions to be checked, right? What are the two conditions? If A is true and if A is false, or if A is 1 and 0. True or false, you can substitute them with 1 and 0. Right? Now, you take the root node as A, and if A's value is true, then what about the B's value? Again, if it is true, the outcome will be true. But if it is false, the outcome will be false. Am I correct? Now, take another branch. If A is false, then B value is checked. If it is true, it becomes false. If it is false, it becomes false. Did I construct the tree correctly, students? Speak out.
Yes, ma'am. Yes, ma'am.
Now, can I trim my tree? Can I make it more simpler? Did you observe something on the right hand side of the tree?
The true and true part.
Yes, Naina.
True and true part.
Yeah, both are false, right?
Like A and B are true. True. Yes, ma'am.
Correct. On this right hand side branch, did you observe? Irrespective of the B's value, the outcome will be false only. Though B is true, it gives the label as false because A is false. And though the though the B is true, it gives false. Though B is false, it gives false again. Means irrespective of the value of B, the outcome label is being false. Now, can I trim my tree like this? A, if it is true, then if B's value also is true, it is true. If B's value is false, it is false. Other side, I need not draw anything if A value is false, because it is always ending up in a false label. This is how I can draw a decision tree for A and B. Now, can I draw a decision tree for A or B? That is also simple, right? Now you knew how to draw a decision tree for A and B. You can draw a decision tree for A or B. And you can draw a decision tree for A XOR B. What is A XOR B? How does the truth table look like? A, B, and what is the result? If both are same values, in that case it will be 0. If any of them is 1, then the value will be 1. Okay, that is the truth table for A XOR B. Now draw the truth table first. If at all it is asked in your exam, draw the truth table first and construct the decision tree. That will be easy for you to validate whether your decision tree is correct or not. Okay, now I am not going to touch on A or B decision tree or A XOR B decision tree. That will be the problem given to you in the exam. So try to understand how to draw decision trees for this kind of Boolean expressions. Okay, so that you can easily answer your innovative question. Sorry, case study question. Okay, in the forthcoming session, we'll go about this, the basic decision tree learning algorithm, which attribute is the best for the classifier, and that we'll understand with an illustrative example. Now let's meet at 2:40 exactly for the quizzes event. Participation is mandatory. All have to participate because that will be taken as your second assignment marks. Your first assignment marks are given for your presentation, right? So your second assignment marks will be given for this quiz. And the top 10 students will be given some relaxation in doing their third assignment. Okay, leaderboard will be given, and whoever comes in the top 10, they'll be given some relaxation, and some perks will be given for the students once the college reopens, right? So all will be there for the quiz event at 2:40. I'll make it live by 2:45. All have to join by that time. Okay, let's meet in the next class.